In section 1.2, we're using segments and congruence. We're going to talk about the word congruent, talking about congruent segments. Remember, the line segment has two endpoints, so it does not go on forever. One of the most important terms that we use in geometry is congruent. Now, congruent is the way that we describe things that are the same or things that are equal. And instead of just using an equal sign, when we talk about actual objects, actual geometric figures, we use the word congruent. And the congruent symbol is an equal sign with this tilde, this squiggle over the top. So this is our congruent sign. It's saying that things are equal, and actually this is like the similar symbol. We'll talk about that in a few later chapters. But we use that congruent symbol when we talk about objects, when we talk about geometric figures. So we're talking about segments and congruence today. Two basic terms that we need to identify because we're going to deal with them all year. First of all, a postulate or an axiom is a rule that's accepted without proof. It's more of a common sense statement than it is a formal rule, because a formal rule is a theorem. It's a rule that can be proved. Theorems, we can use previous postulates, previous axioms, and our undefined terms, point signs, and planes to prove theorems and say that they are for sure true. Postulates and axioms we kind of accept without a formal proof because it seems more common sense. And we're going to start out with a postulate here on the next page. It's called the ruler postulate. This whole postulate sounds really complex, but it's actually really simple. I'll read this to you. The distance between 2 points, A and B, and we write the distance between 2 points just using the two letters A, B, is the positive difference of the coordinates. Now remember, what does difference tell you to do? Difference tells you to subtract. Notice that it says positive difference. Positive, which is why we have absolute value around the x sub 2 minus x sub 1, because absolute value, of course, makes things positive. Difference, we are subtracting the coordinates. What does this mean? If we have a line segment, and we have 2 points on there, let's say we have point A here, and let's say that point B is actually at the very end. If I want to know the distance between points A and B, let's say this is at 0, let's say this is out at 2, and let's say this is out at 7. I said, what's the difference between A and B? The fact that we didn't start A at 0, you would say, well, from A to B I'm going from 2 to 7. X sub 2 is just the second point. We just put the sub 2. X sub 1 is just the first point. And all it's saying is we'll subtract where the second point ended, which is 7, from where the first point ended, which is 2. And you notice you get 5, and the absolute value of 5 is still 5. If I had subtracted in the other order, 2 minus 7, I would have gotten negative 5. And of course, distances, we never do negative, which is why it's an absolute value. So a lot of words, and it looks complex. How do you find the distance between your points? You just subtract their coordinates and make sure you do the positive answer. And another, quick example here. Really, this is if you were sort of measuring, or you didn't have 0 on the first point. So I want to know the length of line segment, PQ, line segment, because there's no arrows, to the nearest tenth of a centimeter. I look at where point P is on this ruler, and it looks like it's at 1.5, I would say. I look at where point Q is on this ruler, and I see that it's at 7.1 centimeters. If I want to know the length of PQ, by the way, with length, you don't put a symbol over the top, because I'm saying from P to Q. I'm not talking about line segment anymore, so I don't put the line segment. I'm just saying distance from P to Q. Notice here when we talk about distance, we don't have the segment over the top. But distance from P to Q, of course, I would do 7.1 minus 1.5 to find the distance between the points. Again, I know this is an absolute value, but if I subtract it this way, my answer is positive, and that's what I want. And I'm looking at 5.6. Okay, so distance from P to Q without the segment over the top is 5.6. That was ruler postulate. Here's a really profound statement. When 3 points are collinear, one is between the other two. And you might be saying, yeah, that kind of makes sense, doesn't it? Remember that collinear, co meaning together, linear meaning on a line. if 3 points are together on a line, there we go, there's 1 point, here's another point, here's another point, 3 points together in a line, one's between the other two. I would say that this one is between the other two. So profound statement, but it does help us come up with this really, really important postulate that we'll use over and over, which is segment addition postulate. Oh, by the way, you know how this was postulate 1, ruler postulate? And now we have postulate 2. I don't care about the numbers don't matter, it's just your book putting them in order. So don't worry about that, just understand the postulate and know that this is ruler postulate, and know that this is segment addition postulate. This we will use all year, segment addition. And just by the name, obviously we're going to be adding segments. That's all there is to this. When you have 1 point between two others, we can add the 2 smaller segments to get the larger. In words, in a formal statement, here we go. If B, which obviously means point B, is between points A and C. Here we do have that situation. Point B is between points A and C. Then AB plus BC equals AC. Remember that when you have 2 letters like this, we're talking about the distance from A to B. Now segment AB, or distance AB would be right here. Plus BC, again the distance from B to C, that segment, that distance is here, would be equal to AC. Now AC is the entire segment. Makes sense. We added this part, AB, that distance, to this part, BC, or that distance, and we get the full segment distance, A to C. This also works the other way. We flip the if and then of this statement. We say if AB plus BC equals AC, meaning if you add 2 parts, 2 segments together, and you get the full segment, notice B was repeated in both of these. If that's true, it must mean that point B was in between A and C, because you added the parts from A to that middle point. And I shouldn't say middle, it's not the middle, but from point A to that point somewhere in the middle, point B, and from that point somewhere in the middle, point B, to C, then A and C were the end points. B was between those 2. Let's use segment addition for something in real life. If you look at a map of Wisconsin, and you look, all of these cities are right on Highway 51. If you go from Tomahawk to Wausau and Madison, they're almost in a perfectly straight line. So I'm going to say that they are in an absolutely wonderful straight line. And we have Tomahawk, Wausau, Madison. And I'm wondering, what is the distance from Tomahawk all the way to Madison if the distance from Tomahawk to Wausau is 40 miles, and the distance from Wausau to Madison is 143 miles. So I'm going to draw a little sketch. Geometry, pictures, and sketches are very helpful. We're obviously dealing with some sort of line segment in this case. I'll draw this line here. We know that Tomahawk is the furthest north. I'll put T for Tomahawk. And we know that Wausau is south of Tomahawk, and then gotta go quite a ways to get to Madison. Alright, so I am told, let's see, what is the distance from Tomahawk to Madison? This is what I want to know. What is the distance from Tomahawk all the way to Madison? If distance from Tomahawk to Wausau is 40 miles, I'm going to put a 40 right here then. That's the distance Tomahawk to Wausau. And the distance from Wausau to Madison, that part of the segment, is 143 miles. And the ultimate question is, what is the distance from Tomahawk to Madison? I want you to tell me this answer when you come into class tomorrow. So that'll be the first thing I ask you. You should have that answer ready, using segment addition. Let's use segment addition in these 2 problems too. Find missing links using the segment addition postulate. Find xz, which again means distance from x to z, since I don't have the segment over the top. X to z. That means I need this entire thing. I went from x all the way to z. Question mark. What is that distance? Well, I know x to y is 23. I know y to z is 48. To get that full distance, I need to do 23 plus 48. Add them together, segment addition. And I get 71. So distance from xz, written just like that, is 71. This second example uses segment addition slightly different. Find CD. C to D is the unknown here. I'm going to put an X there. We don't know CD, but we know that DE is 17, and we know that the entire segment CE is 42. This time we're not adding two segments to get a larger necessarily. We're taking the full segment, taking away a part of it to get what's left. You could write out something and say, well, I don't know X. I don't know the distance from C to D, but I know that if I add X and 17 together, I would get 42. Okay, I know if I add these two parts, I get the full thing. That's what segment addition says. You add two parts of a segment together that are next to each other, and you get the full segment. But of course, you would just subtract 17 from 42 and get your length of CD there. And so we get CD is 25. Again, when you're talking about lengths, you don't do the segment above it. Like the CD is 25, because 25 plus 17 would give me 42 for the entire segment. Alright. Talking about the next really important thing today, congruent segments. I mentioned right at the beginning of this lesson, the symbol for congruent. Congruent is the equals term for geometric objects. It's saying that geometric things or actual figures are equal or the same, and we use that congruent sign. Congruent segments, then, are segments with the same length, the same size, the same distance. So if I knew that ST, line segment ST, and line segment EF were the same length, I could say that those segments are congruent. I could also say their lengths are equal. But there's a big difference between how to say these. First of all, we talked about lengths today. You don't put the segment over the top. S to T, that's the distance. ST is the distance between S and T, and that would be equal to EF. Which, again, if I don't put a line segment over the top, I'm talking about the distance or the length, and I would say that those lengths are equal because the lengths are numbers. If I want to talk about the segments being congruent, being physically the same, then, first of all, I'm using the congruent sign, which is that equal with the tilde over the top, and I'm writing ST as a line segment. Oops, I don't know why I put that so far over, sorry. But I'm writing ST as a line segment over the top is congruent to, and I'm saying line segment EF, because I'm talking about the actual physical geometric objects, and by putting line segment over the top, I'm talking about the object itself, these actual line segments. And again, using the congruent symbol. When I was talking about lengths, no line segment symbol, because I'm talking about the numbers, and the numbers are equal. The numbers aren't congruent, the numbers are equal. Finally, to label that these segments are congruent, if I wanted a visual, symbolic, something that would tell me that these segments are congruent, you put the same number of tick marks in there. So I put one tick mark through ST and EF. That means these segments are congruent because I notice I have the same number of tick marks. If one had two tick marks and the other had one, they're not congruent anymore. If they both had two tick marks, now they're congruent again. So you'll see this throughout the entire year. If you have the same number of little tick marks in segments, it means that they are congruent. Remember, segments are congruent. Lengths, without the symbol, are equal. Example here, plot the points x, y, w, and z in a coordinate plane. I want to know if segment x, y, and segment w, z are congruent. X is at -2, -5. Y is at -2, 3. W is at -4, 3. Z is at 4, 3. Let's see here. X was at -2, -5. Y was at, yep, I did put Y in the wrong spot, sorry. Y was at -2, 3. Thought something looked wrong there. Okay, let's check this out. Our X, Y, I'll do that one in green. And W, Z congruent. Alright, first I'm going to have to figure out the lengths of these segments. This actually kind of uses ruler postulate that we started out this section with. Let's check out W to Z first. Notice W is at -4, and up at 3. So this was 4 in this direction. Z was at 4, 3. So I have 4 on both sides. WZ is a length of 8. X was is at negative 2 and down 5. So there's a length of 5. Y was at negative 2 up 3. So 5 and 3, also a length of 8. Are they congruent? Yes, their lengths are the same, meaning that these line segments are congruent. Again, if I wanted to say their lengths were equal, I would say XY equals WZ. But if I wanted to talk about the line segments themselves with this symbol, then I'm talking geometric figures, and those geometric figures are congruent. So use ruler postulate and segment addition, and talking about congruent segments. And the last one is the best because we get to use some algebra here. Point S is between R and T on line segment RT. Find X, then find RS and ST, and I have an expression for each of these. What should I start with? I think I should start with a picture. So I know we have a line segment here. Point S is somewhere between. That doesn't mean it's in the middle, but point S is somewhere between R and T. So I'm going to put R and T here, segment RT, and S is somewhere in between. Just approximating. Alright, here's what I know. I know that RS equals 2x plus 10. RS would be the distance between R and S, and that's 2x plus 10. I know that ST, which is here to here, is x minus 4. And finally, I know that RT is 21. Now RT would be this entire segment length. This is using segment addition. I have one big segment, length of 21, which is divided into 2 smaller segments. I know that when you have, 2 parts of a segment that combine to a whole thing, you can add the 2 parts together to get the entire segment. That's what segment addition tells you. S was between R and T, so add RS and ST together, get the whole thing. That's what I'm going to do here. I'm going to add RS and ST to get the entire segment RT. Now RS is 2x plus 10. And I know that if I add the other portion of this whole segment, which is x minus 4, so I'm doing 2x plus 10 plus x minus 4, add those together, I get the full segment, which is a length of 21. The setup was all geometry, now it's algebra time. Let's solve this for x. Combine like terms, 2x and x is 3x, 10 and negative 4, so 3x plus 6 equals 21. Let's subtract 6 from both sides. 3x equals 15. Divide by 3, and x equals 5. I did the first part of it, I found x. I also have to find RS and ST. Well, now that x is 5, what does RS equal? 2 times 5 plus 10. Because it's 2 times x plus 10, so 2 times 5 is 10. 10 plus 10, RS is 20. And what does ST equal? Well, it's x minus 4. Again, x was 5. 5 minus 4 is 1. Let's see if this works out. If RS is 20, wow, that's really long. ST was only 1, so point S must have been almost like here. 20 plus 1 is a full length of 21. And we're good to go. So today I'm talking postulates and axioms. We got ruler postulate and segment addition postulate, which are really important in talking about congruent segments.